Well, a very warm welcome to Larry Kaufman. It's fantastic that you're here to join us today and to share your insights into your chess program, Komodo, which we're looking forward to immensely. But first of all, Larry, I was just wondering, can I ask you some introductory questions just so we can get to know you a bit better?
Sure.
Okay. Now, you are, in fact, a real Grandmaster. That's correct, isn't it?
Well, I did get the title legitimately, yes. Whether I'm really Grandmaster strength is a matter of opinion, but I did earn the title, yes.
A lot of Grandmasters I know, they become Grandmasters at sort of 18 or something like this, but you didn't, did you? I don't think.
No, I only got the Grandmaster title at the age of 60, but it's because I was 60. The point is I had been an international master for nearly 30 years. And when I turned 60, that was at that time the age requirement to play in the World Senior Championship. Now they changed it to 50 later, but it was 60 at that time, which that year was 2008.
Yeah.
And the winner automatically gets the Grandmaster title. So I went to the tournament hoping that somehow I would pull off a miracle and win it and get the title. And that's exactly what happened.
Well, congratulations. I mean, that gives me hope that there's still time left. If I get to International Master or even FIDE Master, I'll be over the moon. But you got to Grandmaster. That's fantastic. But you're not just a Grandmaster. You're also the author of innumerable books. Here's mine. Which way around is it? Yep. One of your latest ones. And there are numerous others as well. So you do that, but you've also got your own chess program, which you're the co-author of. Is that correct?
Yes, that's correct.
And we're here to discuss that today because Komodo, well, it's really sort of Komodo. What are we calling this, by the way? Komodo Dragon or Dragon by Komodo or?
Yeah, I mean, it was just Komodo up until we added this NNUE about 3 years ago. And then we thought that was such a big change that it needed a new name. So at first we just called it Dragon by Komodo, but everybody's just calling it Komodo Dragon, so we stopped fighting it.
Yeah. I mean, that sounds to me like the best name. Now, I would really love to get all the listeners on board with this because I think you've got a very unique engine. It's extremely strong, isn't it? I mean, you're biting on the heels of Stockfish by just a few elo points, and that is a considerable achievement considering the team and resources that they've got. Well, you were just two actually, but now, as I understand it, there are a few more people to the team. Is that correct?
Yeah, there's only two of us that are more or less what you might call full-time, but there are about three others that you would call part-time.
Okay, great. Now, let's just try and get clear what makes Komodo so special. So if we could rewind the clock, back to the old days where everybody had an engine which was alpha beta, and all of the alpha beta engines had a hand-tuned evaluation function. So just to try and explain it for everyone, is it fair to say that a chess engine has got two parts to it? Is there anything I'm missing there? You've got a search part and you've got the evaluation function. Have I got that right?
Those are the two components after the opening is over. And there's also the in-game table basis. So there are actually four components.
Okay, yeah. And could you sort of briefly try to describe for us what is alpha beta search?
Okay, so that alpha beta search was developed roughly around the year 1960. Originally, when computers started to play chess, or at least when they started writing computer programs to play chess, which was maybe the late 50s, so they would just try to look at every possible move and work out, what's the best move. But somebody around 1960 made this what now looks like an obvious discovery, but apparently it took them a while to realize that you don't need to look at every move, because let's say, for example, I'm trying to, let's say we're in the opening position And I've analyzed the move E4, and I've concluded that it gives white a 0.15 advantage or whatever. And then I move on to the next move, D4. And the first move that I try against D4, let's say is D5, and let's say that I conclude that that only gives white a 0.12 advantage.
Okay.
Well, at that point, we don't need to look at other moves for black because it doesn't matter how bad D5 is. We've already proven that it's not the best move.
Okay.
So alpha beta is all about ignoring moves that have nothing to do with the choice of what is the best move.
Okay, makes sense. Right. Now, that will be relevant to our discussions probably later on when we talk about the Monte Carlo search. But the other side probably we ought to just touch on is the evaluation function. Now, as I understand it, you're something of an expert at knowing the exact piece values, which go quite a long way beyond the sort of, the regular thing we're taught as children, where rook is worth 5, a queen is worth 9, and all that kind of stuff. How would you, as an expert, put together a hand-tuned, a human-tuned, or human-created evaluation function?
Okay, well, that's sort of two questions in one. One of them is about material.
Okay.
So up until almost the turn of the century, of course, many grandmasters over the years have expressed opinions about it. Like Bobby Fischer said that I think he said a bishop was a quarter of a pawn better than a knight, or everybody has opinions about it. Larry Evans wrote, I think a bishop is 3.5 and a knight is 3 1/4, and so forth. But up until the turn of the century, it was just opinions. But
Right.
in I think it was 1999, I wrote an article in Chess Life magazine where I did a database study, which was only becoming possible at that time. They didn't even have databases until a few years before that. So I did a database study to try to actually determine what the values of the pieces really were in actual practice. And I mean, basically, it wasn't too different than what authors had said. It showed that a knight is a little better than 3 pawns generally, and a bishop is a little better than a knight. However, the biggest thing that I discovered was that it's not so much that a bishop is better than a knight, it's that 2 bishops are a big advantage. Now I mean, people have said that too, but I think even when Bobby Fischer more emphasized bishop being better than knight as opposed to the value of 2 bishops. And my study showed the big deal was having the 2 bishops, not just the bishop versus knight difference.
Yeah.
So that was one discovery I made, and then of course I worked out how much the exchange is worth, what 2 minor pieces versus a rook, all that sort of stuff. But there's 2 parts to this. You can talk about the average values of the pieces, but you can also say that they're not constants. They change during the game. So I did work out a set of average values, but I also worked out how they are affected by the game stage. For example, the relative value of rook versus minor piece is the minor pieces are a little better in the opening, and the rooks are a little better in the end game. So, and the number of pawns on the board affects, more pawns is bad for rooks, and few pawns is good for rooks, that kind of thing.
Yeah.
So I was eventually able to work out pretty well how the values of all the pieces depend on what pieces are on the board. But that's only the first part of an evaluation function. Evaluation function has to think about things like mobility and king safety and pawn structure. So it's a very, very complicated thing. And it used to be just the opinion of the author. I mean, when I did the programs I did with Don Daly back around 1990, like Rex Chess and Socrates, it was basically just my opinions of what the bishop, what a double pawn should be, or what a open file is worth, all that sort of stuff. But later on, we started to be able to actually get data on this. It ceased to be purely a matter of opinion, and it started to become more scientific. Now, when I was working on the Ribka program in 2007, I pretty much assigned all the values for well, it was Ribka 2, the final Ribka 2, which was 2.32a.
Yeah, I remember that.
That had all of my, basically my opinions about everything in it.
Yeah.
And then we started to tune my numbers with actual testing, so that by Ribka 3, it had my values, but modified based on what actually improved the results of the program in test games. So that was the next stage of it. And then I started to work on the Komodo program, again with Don Daly after a gap of about 15 years. We worked on that together until his unfortunate early death in the year 2013,
yeah.
At which point Mark Leffler took over Don's role. And so there, when the evaluation function, it was getting more and more sophisticated and less intuitive, because what we discovered was that the testing often showed that things that are intuitively weird actually work. So we, for example, it particularly had to do with king safety. We found, and the sockfish people were making the same discovery independently. We were both discovering that unreasonably high values for things relating to king safety or the possibility of giving checks work. I mean, it's intuitively, like if you're a teacher and you're teaching a student, and you say, okay, here's a position where white can give a check, but black can just move out of it. You say, well, that's not a big deal. I mean, just having the right to give check is no big deal. If you can't follow it up, who cares?
Yeah.
But the programs do think of it as kind of a big deal, because their experience is that in general, having your king subject to being checked or attacked, sooner or later, it's going to matter.
Yeah.
And so the computers will often say that a slightly weak exposed king is worth a pawn, even though a grandmaster would look at it and say, that's ridiculous. You don't give up a pawn just because you might have a check someday or something. That's silly. So that was a big thing, trying to get used to that. And I think it was interrelated to search, because the search that we use in more recent days has been a tapered search, meaning we look at fewer and fewer moves near the end. And I think the consequence of that is that the program has to become more paranoid about threats to its king, because if it can't look at all the moves, it has to say, oh, well, maybe I'm missing something. I better be sure that my king is safe.
That tapered search at the end, is that what they call late move reductions?
Well, late move reduction leads to that. That's not what they call it. There's also late move pruning.
Okay.
And they both of these things lead to looking at fewer and fewer moves near the end of the search.
Okay, interesting. I clearly remember when you came on board with the Ribka team, and then version 2 started to go up, and then version 3. That was just incredible when that came out. It was just sort of head and shoulders above every other chess program on the planet. So that was we were in awe at that time. I have very clear memories of that and how wonderful that time period was. Given that you've got all of this expertise and you brought it to bear upon the different chess programs, what was it like for you when AlphaZero arrived, both with a different search and a different evaluation function? That must have been a bit odd. And now clearly you've taken things off in a slightly different direction, but nevertheless, that was a revolutionary moment for the chess world. What happened there with AlphaZero?
It was a big shock, yes. Of course, first they did it with Go, and being a Go player, I already appreciated what an amazing achievement that was. So the two things are not unrelated. I mean, they introduced neural networks, and they introduced the Monte Carlo search, but there's a reason that they did both. It wasn't just like two unrelated ideas. The point was that the neural networks are very slow to compute, and really to do them at a decent amount of time, you need these GPUs, graphic processor units, and the alpha beta search relies on looking at millions of nodes, and the neural networks were just too slow to be consistent with that. So they had to come up with a type of search that would work with much smaller number of nodes.
Huh.
And that's why they came up with this idea to use Monte Carlo. Now, I should explain that Monte Carlo, originally when people talked about Monte Carlo in programming, they meant just having the program play out the game thousands of times and like play the move that won the most games. But what we actually do now is different. It's called Monte Carlo tree search, where it doesn't actually play out the games. It just searches the tree in a manner that's somewhat random. Somewhat, I say, not totally. And so it's not fully playing out the games. It's just playing out variations in a statistical manner, and basically trying to determine which moves statistically look like they're going to get us the best results without actually playing entire games. So it's not Monte Carlo in its original sense. It's a kind of a hybrid idea.
And did AlphaZero use Monte Carlo in its original sense or in the tree search sense?
They use Monte Carlo tree search.
Okay. How does it explore then if it doesn't play out the full game? How does it know how well the search is going?
Well, basically, the simplest way to look at it is, suppose you're using Monte Carlo tree search together with just a regular engine.
Yep.
Like the kind we used to use.
Yep.
Okay, and you can do that, and we did do that, and you can do that with Komodo if you want to turn off the neural network evaluation and use our Monte Carlo version. What it does is it will, every time it reaches a node, it'll select a move semi-randomly. By semi-randomly, I mean it won't necessarily pick the best move, but it'll have some kind of a rule for choosing based on how many times it's tried each move and what the assessment of each move is. So it's still going to play good moves much more than bad moves, but it will try bad moves eventually.
Okay.
And then it just plays it out until time runs out, and it says, okay, we got to draw a conclusion, and we have an evaluation function. Here's our evaluation.
Yeah.
But instead of doing what alpha beta does, which is assume that each side will always play what it believes to be the best move, it backs it up statistically. It says, well, we tried this move 17 times, and this move 3 times, and this move 2 times. So out of the 22 moves, what is our average score? 0.73 or whatever it is. Yeah. So it's statistical instead of just always saying we always know the truth. Alpha beta pretends to be God. It pretends to know everything.
Okay.
Monte Carlo is much more humble.
What are the pros and cons of alpha beta versus Monte Carlo tree search? Because I imagine in some scenarios one might be very superior to the other. Can you talk a bit about that?
Well, alpha beta is certainly superior in situations where everything is forced or clear. Like if you have a mate in 17,
yeah,
you want to use alpha beta. You don't want to do probabilities. You want to prove this is mate in 17.
Okay.
But if you're in situations where everything is gray and vague and you just don't know which move is best for each side, then alpha beta isn't so great because it pretends to know which move is best, and that's not perhaps very realistic. So that's where alpha beta, I mean, Monte Carlo looks better in gray positions.
Okay, and to be fair, that is a lot of chess, isn't it? I mean, you come out of the open,
yeah, big part of
pretty
chess.
great. Yeah. Okay, so when we talk about Monte Carlo today, as opposed to 4 or 5 years ago when AlphaZero was around, the first thing that comes into my mind is LC0, Leela, because they use Monte Carlo, don't they, with theirs? But that is using a GPU to open up the neural net, and then the CPU is doing some searching. But your Komodo Dragon, which has a MCTS function or a checkbox that you can tick, so it uses that type of search, doesn't use the GPU, does it? It's only CPU based. Is that right?
That's right. But the reason has to do with this other big breakthrough in technology, which is called NNUE.
Right.
Now, NNUE came along about what was it, two or maybe 3 years ago. It was developed by Japanese who were playing the game shogi, the Japanese version of chess, and shogi programs had been coming along just like chess programs. They were a few years behind. I mean, they didn't reach parity with the best humans until roughly a decade after when it happened with chess.
Okay.
But the shogi programs were very, very good. And of course, when AlphaZero came out, and AlphaZero even had a shogi program, so that was all very impressive. But they got the idea. One Japanese in particular got the idea that maybe it's possible to have your cake and eat it too. Okay, and because the GPUs that are used for neural networks, there's a huge overhead in communicating between CPU and GPU. They just can't look at millions of nodes per second. It just isn't possible.
Yeah.
So, but if you only use a CPU, you can only do it. You can't look at a big neural net. It's too slow. You can only use a tiny net. So, but they came up with the idea that maybe if you use really tiny nets, you can still get a lot of the advantages of AlphaZero or LC0, which is basically just the PC version of AlphaZero. Maybe you can still get a lot of the advantages, but have it be so fast that even the CPU can still run regular alpha beta at a pretty high speed.
Okay.
And that was proven in shogi. And the author of the shogi program, his program relied a lot on stockfish, so he felt some kind of obligation, and he said, the stockfish people should try this, because in his opinion, he said he thinks it would add 100 elo to the chess program. Well, he was right. He was very right. But as soon as I read about this, I also recognized that it was probably true. I believed him, and we started talking about it, and okay, stockfish beat us to the punch by a couple of months, but we also soon had an NNUE version of Komodo Dragon, and what these NNUE programs do, whether it's stockfish or Dragon, doesn't matter. What they do is they use a tiny neural network to evaluate the position instead of the old handcrafted evaluation.
Yeah.
So the evaluation is much, much better because the neural network uses the concept of similar. That's the big difference. See, a handcrafted evaluation is very, very concrete. It says, okay, if the rook is on the 4th file and the pawn is on A7 and this or that and that, you do this. It's very, very specific. But neural networks can recognize the concept of similar. They can say in similar positions, E5 is usually a good move. Or in similar positions, white is usually better if he has a knight on F5, that kind of thing.
Yeah.
And because of that similarity idea, that makes their evaluation much more reliable and accurate than any handcrafted evaluation can be.
Even though, as you've just said, the NNUE is quite a small network, even then it's superior.
Well, that's the thing. It's not nearly as good as a big net, but it's still a lot better than no net.
Yeah. Okay. Wow, that's pretty clear. That's pretty good. So LC0 therefore uses a massive net, which means it has to use the GPU to open these nets up. Is that right?
Yeah, I mean, it will run. You can use smaller nets, and it'll run on a CPU with a intermediate size net, let's say, and it'll still play very, very good chess, but it won't be at the level of Stockfish or Dragon.
No, of course. Yes. Okay. Now, where have you gone rather with Komodo? Because you've got an alpha beta search, which is kind of like the default version, but you've also got this interesting Monte Carlo tree search option as well, and you've got a neural net. So how do those two work together?
Okay, so I'm pretty sure we're the only program in the world that combines NNUE with Monte Carlo tree search, because we had the program that uses the NNUE with these small nets with alpha beta. But I figured, why not at least see what we can do with the Monte Carlo tree search, but still using alpha beta as well. So the way we do it is we each time we get to a node, if instead of calling a big net, we call a short alpha beta search with the small nets evaluating the positions at the end nodes. So
wow. So it's like some kind of hybrid approach.
It is a hybrid. It's definitely a hybrid. Yes. Okay. So each node is a short alpha beta search with NNUE evaluation. But then once we do that evaluation or that short search, that just becomes a node in the Monte Carlo tree search. And so the Monte Carlo tree search itself is similar to what AlphaZero or LC0 uses. I say similar because it's substantially different. I mean, we don't just copy their code. It wouldn't even make sense. I mean, it's too different. We have to do things quite a bit differently for it to play well.
Okay.
But the concept comes from them.
Right. I want to make sure I've got this because this is breaking my brain a bit, but I think that's fascinating. So the Monte Carlo tree search in Komodo Dragon does little alpha beta searches as it encounters each node. Is that what you're saying?
Yep.
Okay. And would that explain the relatively low node count that you see on the screen when you've got MCTS enabled?
Right, because we're only displaying the Monte Carlo nodes.
Yes.
If we wanted to impress people with our node count, we would report the number of nodes looked at in the short searches, and then it would be back up in the millions again.
Okay, so when you see those little numbers on your screen, it doesn't mean that Komodo Dragon is broken. It means actually it's just working absolutely right.
Yes.
Okay. I'm fascinated by this. Can you explain the changes in nodes per second that you see when you change hardware? So for example, on my laptop, I was shocked the first time I tried it because it was something like 90 nodes per second. I've got an AMD Threadripper, it's a much bigger machine, and that was in the thousands. Is it just a case of bigger hardware produces more nodes per second, or is there some kind of scaling going on where you do different things according to the number of threads employed?
Yes, we do. We do different things according to the number of threads. We just found from testing that with more threads, it pays to look at more nodes per second, but smaller ones. I don't even know if I can explain why that is true, but that we found if you only have one thread, it just doesn't seem to work very well to use tiny nodes. We have to use pretty big nodes to get a good quality.
I see. And does Monte Carlo as a, I don't know if it's even worth talking about standard Monte Carlo, but the type of Monte Carlo you're using, how does that scale with time? Because we know with alpha beta, you double the time and you can pretty much predict the type of elo gain that you're going to get back, or at least you could do until recent years where everything seems to have been a little bit broken with chess. But with the older programs, it used to be fairly well established that if you double the time, you get about whatever it is, 40 to 60 elo points return. Does Monte Carlo scale in the same way, or do you get diminishing returns or better returns than with alpha beta? Oh dear, I think I've lost.
General impression there is that they perhaps don't scale as well because it looks like once you get beyond, I don't know, a few thousand nodes per second, they don't get quite as much benefit out of each doubling anymore. It's sort of like after a while they just say, this is the move, I'm going to stick with it, you're not going to convince me otherwise. It's
right.
kind of like that.
Yeah. Because a lot of people say that about LC0. It doesn't change its mind very often.
Right, and that's what's going on. But the difference is with Komodo Dragon MCTS, our nodes per second that we report is a much smaller number to start with because
dropping out.
It's likely we would also hit diminishing returns eventually, but we don't get up to 20,000 nodes that quickly. I mean, on Monte Carlo, so it looks at practical time limits we scale quite well.
Okay, that's fantastic. Right. So then let's get to the real meat of what of where we're going here. You've done a marvelous job of explaining how your program is totally unique. It's like it's got, I mean, would you say it's almost like the best of both worlds? We've got the accuracy of alpha beta, but we've also got this ability to navigate the gray space, which Monte Carlo can do, which so much of chess, especially the opening, you've got that as well. So would you say it's the best of both worlds?
Well, we try to offer both options so that you can use whichever one is appropriate for your, either for the position or for the situation you're in. It depends what your purpose is and how you're using it there. So yeah, there's a good reason to offer both, yes.
Okay, so then let's take a real world example. You're preparing for an opponent in a tournament coming up, and you've got a fairly good idea. You're doing some opening preparation, perhaps. I think probably most people now have learnt that they don't just go straight to an old version of Fritz. They know better than that these days, and the younger players would go to Stockfish. But actually, what you've got here is an edge even on Stockfish for practical purposes, because humans are suboptimal creatures. We don't play perfectly. We're not God. We make mistakes. And a lot of chess, as we've said, is operating in that gray space. So how can Komodo Dragon put pressure upon my opponent in a way that a traditional alpha beta searcher maybe doesn't do quite as well?
Well, basically the alpha beta search, whether it's, doesn't matter if it's Stockfish or Komodo Dragon, it assumes that the opponent is just as good as it is.
Yeah.
And we'll see everything that it sees. Now, if you're playing correspondence chess, that's probably a good thing to assume. But if you're preparing for a human opponent in an over-the-board tournament, even if he has prepared a little bit with his computer, he's not going to be able to remember 50,000 variations in his head. I mean, he's going to have to think for himself pretty soon. Yeah. And he's going to make mistakes. I mean, even the best humans, as we see constantly, make terrible moves in tournaments. There's no denying that. And the problem with using an alpha beta search is that it will assume that the opponent will never make a mistake, and so therefore it will never play a move that gives you a better practical chance. It just, even if it thinks there's some very, very subtle refutation 17 moves down the line that makes this move be a tiny bit suboptimal, it will just reject it. but with Monte Carlo search, whether it's ours or AlphaZero, the advantage of Monte Carlo search is that it's probabilistic, it's statistical. So it will basically, it'll play the move that will score the best against intelligent but not perfect play.
Right. Now, to put this into kind of like layman's terms, it sounds to me almost like you're saying Komodo will find trickier moves or more testing moves that really put the opponent under pressure. Is that fair? If they're suboptimal, if they're human?
Yes, I think that is a pretty accurate description of what Monte Carlo tree search does. It tries to pick moves that are where there's a greater probability that the opponent will go wrong.
I mean, I don't want to lose how massive this is. This is a massive thing. There are so many chess players out there who want an edge over their opponents. And this program that you've got effectively gives them the tools to do just that. We can come up with trickier moves, but they're also sound, because Komodo Dragon wouldn't come up with something that was stupid. They're also sound, and they're going to be really, really useful for people's preparation. Is that fair?
Yes, and because because of our hybrid approach, you can say that it's more likely to only play sound moves that are tricky. Like AlphaZero is a little bit more emphasis on the tricky and a little bit less on the sound.
That's fantastic.
We're compromised. We try to, anything we play is going to be. It's going to be sound in the sense that it may not be sound in the sense that that Stockfish would necessarily agree that it's the best move, but it'll be sound in the sense that any opponent, at least up to 3,300 level or something, will have to agree that it's sound.
Yeah, got it. What advice would you have for people who want to? I'll make sure that your website is included in the video, so we get all the people will find it easy to buy Komodo. But what advice would you give people on the hardware side? I mean, we've already touched on this idea that bigger hardware gives you better results. Is it a case that, I don't know, 32 threads would scale twice as well as 16, or in terms of strength? Do you have any data on that, how the scaling performs?
Well, it's changed recently. I mean, a few years ago, before NNUE, there was more of a need for really powerful hardware. It's still desirable, but it's gotten to the point now where if you got, a good computer, like, something with maybe 8 cores or whatever, the benefit of getting more is pretty small if you're using a top program,
Okay, and the benefit is pretty small going from, even with Komodo MCTS. That's what we're saying, isn't it?
I mean, it's a little bit more with the MCTS than without, but I would say that unless you're playing correspondence chess where you're just trying to, get a tiny edge every 20th game or whatever, it's the benefit of going from 8 to 16 cores, let's say, is for use against practical human opponents over the board. The benefit would be pretty tiny.
Okay. Just to finish off then, is there anything else you want to talk about? I mean, I suppose one thought that crosses my mind, and I don't want to cause you to reveal your hand if you want to keep your trade secrets, but have you got any future ideas of development coming up? I mean, it's clear to me now that using the GPU probably isn't on your radar because of the reasons you've already given. I don't know if that's true or not, but have you got any ideas of how you'll develop Komodo Dragon further?
I mean, I wouldn't rule out GPU. It's not obvious right now that we would get much benefit by using it, but that doesn't mean that somebody won't figure out a way to use it in the future.
Okay.
So I wouldn't rule it out, but that's not on our short-term list. We're putting a little bit more emphasis into things that are, let's say, relevant for the human user. I mean, we're still trying to beat out Stockfish, and we're getting a stronger version every few weeks. We have a new upgrade, and the progress is not stopping by any means. But we've hit a situation now, and this is not just us. This is top level computer chess. This is Stockfish and Dragon and maybe AlphaZero also. We've reached a situation now where it's getting almost impossible to improve the play in terms of how they play the standard start position from chess.
Yeah.
In other words, if both players play good openings, the result is going to be a draw. I mean, when Stockfish versus Dragon, it's already like 99% draws as long as it's fairly good hardware and not too fast a time limit.
Yeah.
It doesn't mean they play perfectly. It just means they play perfectly enough not to exceed the bounds of what can be drawn. Yeah. But all of these top engines still play imperfectly in the sense that if the opponent makes some move that crosses the line into losing territory, but just barely, where it might have to play 17 moves in a row to prove that they have a win, they're not necessarily able to do that yet. So we still have plenty of room to improve in terms of being able to find wins that are extremely hard to find.
Okay.
And there's also plenty of room in terms of practical chances. In other words, even if you're losing, how do you put up the best resistance? How do you minimize the chances of loss?
Yeah, that would be interesting. And
Yeah,
I've noticed sometimes when I'm playing around with Komodo MCTS, it doesn't always find the shortest mate. Do you know why that is? Whereas with Komodo, with its classical search, we'll, get it like that.
Well, that would make sense because it's not trying to find the truthful best move. It's trying to find the move that gives it the highest chance of winning the game. So, they're Russian. There's an old Russian thing they used to say that a Russian grandmaster would rather win a piece than do a mate in 7 because he might be overlooking something in the mate in 7, but he knows how to win with an extra piece. I mean, that's sort of an exaggeration, but there's a point to the story.
Okay. So, in terms of just to round things off, in terms of purchasing Komodo, I believe you offer a couple of different options on your website. One is you can just buy the program outright, but there's also some kind of year subscription, which is the one I use, and I think that's probably the better one. Do you want to comment on those two for any listeners so that they know which one to pick?
Well, basically, the subscription is for people who want to have the best and don't mind spending a few extra dollars. Have it. I mean, if you're going to upgrade it every time we come up with a new version, which is roughly every 2 to 3 months, it would cost you a lot of money if you don't have a subscription. So you definitely want to have a subscription if you would do that. If you don't really care whether your program is up to a year out of date, then just buy the best one once a year.
Great. Larry, thank you so much. It has been wonderful to have this interview with you and your enormous knowledge in this subject and just being involved in the most exciting chess program in the world, I think. We look forward to seeing the developments in the future, and we wish you the very best of luck with your development in this area.
Well, thank you very much. It's been a very enjoyable interview.
Okay, take care. Goodbye.
Hey, bye-bye.